8 minutes ago, on a mountain in Chile, a telescope the size of a small building captured an image unlike anything any human telescope has ever produced. And before I tell you exactly what's inside that picture, stick with me until the very end, because the final part of this story is something almost nobody online is discussing yet. It's going to change the way you look at the night sky forever. Let's start with the fundamentals, because you need to understand what this machine actually is before you can grasp why the entire astronomy world is buzzing about it. This is the Vera C. Rubin Observatory. It sits atop a mountain called Cerro Pachon, high in the Chilean Andes, in one of the driest and darkest locations on the planet. Astronomers picked this exact location deliberately. No clouds, no city lights, no moisture in the air to blur out the stars. It's essentially one of the best possible spots on Earth for peering into deep space. Now here's where things get interesting. This observatory isn't just another telescope perched on a hilltop. Its main mirror measures 8.4 meters across, nearly as wide as a tennis court is long. Attached to that enormous mirror is a camera, and not an ordinary one, not even a professional grade one. This is the largest digital camera humans have ever built. It packs 3,200 megapixels. Consider that for a moment. Your smartphone camera has roughly 12 to 50 megapixels. The single camera has 3,200. Every photo this telescope captures is so massive, so detailed, that displaying one full resolution image would require 400 separate 4K televisions lined up side by side just to show a single picture. And here's the part that truly demonstrates what this machine can do. This telescope doesn't take slow, deliberate photos occasionally the way older telescopes did. It moves quickly. Right now it's capturing a brand new, highly detailed image of the sky roughly every 40 seconds. 40 seconds. Then it swings toward the next section of sky and repeats the process. All night, every night, snapping about 1,000 images nightly for 10 straight years without pause. Why 10 years? Because the real purpose behind this observatory, the goal everything has been building toward for 2 decades, is called the Legacy Survey of Space and Time, or LSST for short. The plan is almost hard to fathom. Rather than capturing a single snapshot of the universe, Rubin Observatory is scanning the entire southern night sky in ultraviolet, visible and near-infrared light repeatedly, every 3 days, continuously, for an entire decade. Stitch those images together, and you don't just end up with a picture of the universe. You get a movie, a genuine, real movie of the night sky changing in real time, built from actual observations, not animation, not simulation. Scientists on this project have literally described it as the greatest cosmic movie ever made. And on June 30th, 2026, that movie officially began rolling. But before we get to what's happened since then, let's back up a bit, because this observatory carries a deeply human story behind its name that most people online never mention. The telescope is named after a woman named Vera Rubin. She was an American astronomer who, decades ago, studied how galaxies rotate. She noticed something odd. Galaxies were spinning in a way that shouldn't have been possible if you only accounted for the visible matter inside them, the stars, gas, and dust we can actually observe through a telescope. Based on visible mass alone, the outer edges of a galaxy should spin far slower than the inner regions, the same way planets far from the sun move more slowly than planets close to it. But that's not what Rubin found. The outer stars in these galaxies were spinning nearly as fast as the inner ones. Something invisible had to be out there, contributing extra gravity, holding these galaxies together from the outside in. Her careful patient work became some of the strongest evidence scientists had for the existence of what we now call dark matter, a mysterious substance that emits no light, that we can't observe directly, yet appears to make up a massive share of the universe's total mass. Vera Rubin devoted her entire career to being precise, careful, and completely committed to simply observing the sky and trusting what the data revealed. So, when the National Science Foundation and the Department of Energy built the most advanced survey telescope in history, they named it after her. It's fitting, because in many ways this observatory exists to continue the work she began, chasing answers about dark matter and its strange counterpart dark energy, the mysterious force that appears to be driving our entire universe to expand faster and faster with each passing year. Before moving forward, it's worth understanding how this camera was actually constructed, because the engineering behind it is its own remarkable story. The LSST camera, the heart of this entire observatory, was built by the U.S. Department of Energy's SLAC National Accelerator Laboratory, working together with teams from around the globe. It's roughly the size of a small car and weighs around 3,000 kilograms, yet it has to operate with such precision that it can capture faint, distant light without the slightest vibration throwing off the image. Inside are 6 large optical filters, each designed to capture a different band of light, from ultraviolet all the way to near-infrared, allowing scientists to study everything from hot young stars to cool, faint, distant galaxies within a single coordinated survey. Every image the camera captures must pass through layers of calibration, checking focus, exposure, and alignment before becoming part of the official dataset. This is why the commissioning phase took as long as it did, because a mistake at this stage could ripple through 10 years of observations. The team behind the project has been transparent about this. They've stated that the decision to officially begin the survey came only after a thorough operational review covering image quality, survey speed, system uptime, reliability, and calibration accuracy. Because once the 10-year clock starts, there's no going back to correct small errors. All that raw data doesn't just sit on a hard drive somewhere in Chile. It travels to the United States, to a data facility hosted at SLAC National Accelerator Laboratory, where it becomes available to the broader scientific community. One of the major science teams working with this data is the Dark Energy Science Collaboration, a group of researchers spread across the globe using Rubin's observations to make highly accurate measurements of the universe's fundamental properties. The precise figures describing how fast the universe is expanding and how matter is distributed across the cosmos. What sets this project apart from nearly anything before it is that this data won't be locked away behind closed doors. Scientists have said this marks the first time this much astronomical data will be available to so many people simultaneously, opening the door for researchers everywhere, not just at major institutions, but anywhere in the world, to take part in genuine cutting-edge discovery. Even members of the public will eventually be able to explore portions of this dataset themselves, essentially gaining hands-on access to a wealth of information that used to belong solely to professional astronomers, with access to the world's largest telescopes. Now, let's walk through what actually happened, step by step, using real dates and real figures. On June 23, 2025, in Washington, D.C., the team behind Rubin Observatory held a public event called First Look. This was the moment the world got its first glimpse of real images captured by this telescope, and they didn't disappoint. One of the very first images released was a composite of two glowing nebulae, clouds of gas and dust in deep space known as the Trifid Nebula and the Lagoon Nebula. Other telescopes have photographed these clouds before, but never like this. That single image was assembled from 678 separate exposures, captured over roughly 7 hours of observing time. In total, that one image contained about 2 trillion pixels of data. 2 trillion in one glowing photograph of colorful cosmic clouds, with enough detail to zoom in endlessly and keep discovering stars hidden inside dust that older telescopes simply couldn't resolve. Another image released that same day showed a section of the Virgo cluster, an enormous collection of galaxies. In that single frame, you can see countless galaxies scattered across the background, spiral shapes, elliptical shapes, glowing quietly behind bright foreground stars from our own Milky Way. Scientists expect that over the full 10 years of this survey, Rubin Observatory will help catalog roughly 20 billion new galaxies. 20 billion galaxies currently sitting out there in the darkness, unrecorded, waiting to be captured by this camera. But here's what genuinely stunned scientists, even the people who built the thing. In just over 10 hours of test observations, before the actual survey had even officially started, this telescope had already captured millions of galaxies and Milky Way stars, and had already spotted thousands of asteroids within our own solar system. 10 hours. Most observatories take years to build a catalog like that. Rubin managed it in less than half a day of testing. After First Look, the team didn't pause to celebrate for long. They moved straight into commissioning, fine-tuning the telescope, testing every component, making sure the optics, the camera, and the data pipelines were all functioning exactly as intended before the actual 10-year survey could officially begin. During this testing window known as the early optimization surveys, something remarkable occurred. In just about 6 weeks, using nothing but this early test data, astronomers working with Rubin Observatory discovered over 11,000 brand new asteroids that had never been recorded before. 11,000 in 6 weeks. That stands as one of the largest single batches of new asteroid discoveries ever submitted to the International Astronomical Union's Minor Planet Center, the official worldwide body responsible for verifying and cataloging small objects across our solar system. Within that group, scientists identified 33 near-Earth objects. Asteroids, whose orbits bring them relatively close to our planet. None of these newly discovered objects pose any danger to Earth, but tracking near-Earth objects remains one of the most critical tasks any observatory can perform, because the more we know about them, the better prepared we are for the future. On top of that, Rubin's early data also uncovered 380 new trans-Neptunian objects, icy bodies orbiting far beyond Neptune, out at the cold, distant edges of our solar system, where sunlight takes hours just to arrive. 2 of these newly discovered trans-Neptunian objects have extremely elongated orbits that carry them nearly 1,000 astronomical units from the Sun at their farthest point. 1 astronomical unit equals the distance between Earth and the Sun, meaning these 2 objects travel almost 1,000 times farther from the Sun than we do. That's deep, remote territory. Researchers believe studying orbits like these could eventually help confirm or rule out the long-debated theory of a hidden ninth planet, sometimes nicknamed Planet 9, 5 to 10 times more massive than Earth, possibly warping the paths of distant outer solar system objects. One planetary scientist involved in the project has said that even if Rubin can't spot the planet directly, discovering more objects with warped orbits would still be an important clue pointing toward its existence. That same early batch of data also allowed scientists to refine and correct the orbits of more than 80,000 already known asteroids, objects tracked before, but whose paths through space weren't fully precise. With Rubin's frequent, detailed observations, astronomers sharpened those orbital calculations, making our entire map of the solar system more accurate than ever before. Then, in January 2026, something else caught the astronomy community's attention. Using data gathered during the first look period, scientists published the very first peer-reviewed scientific paper based on observations from the LSST camera itself. What they found was genuinely record-breaking. Buried in the data was the fastest spinning asteroid larger than 500 meters wide ever recorded, sitting quietly within the main asteroid belt. Researchers said an object like this simply couldn't have been detected without the unique speed and sensitivity built into Rubin's camera. One deputy head of the project explained that discovering thousands of new asteroids in such a short window and learning this much about them is only a small preview of what the full 10-year survey will reveal. Then came the moment that truly opened the floodgates. On February 24, 2026, Rubin Observatory issued 800,000 alerts to astronomers in a single night. 800,000 separate events flagged in one night alone. New asteroids appearing, stars suddenly exploding as supernovae, distant supermassive black holes flaring as they feed on surrounding material, and variable stars whose brightness rises and falls over time. Astronomers called this the true beginning of the alert stream, one of the final milestones standing between the observatory and the official launch of its 10-year mission. And that mission officially began on June 30th, 2026. The Legacy Survey of Space and Time launched following years of construction, testing, and a thorough operational review of technical readiness, data quality, and calibration accuracy. From that night onward, Rubin Observatory began scanning the entire southern hemisphere sky repeatedly every 3 days, collecting close to 10 terabytes of data every single night, with some estimates placing that figure even higher once the survey reaches full operating speed. Across the full 10 years, the observatory is expected to generate roughly half an exabyte of information in total, an amount so enormous that entire teams of scientists and engineers have spent years developing the algorithms needed to sort through it. Scientists have said the amount of data Rubin gathers in just its first year alone will exceed everything collected by every other optical observatory on Earth combined. Not close to it, greater than all of them put together. Once the survey reaches full capacity, the system is expected to send out as many as 7 million alerts every single night. 7 million. And each one represents a real change happening somewhere in the sky. An asteroid shifting position, a star exploding, a black hole flaring, a distant galaxy changing in brightness. One of the deputy directors of Rubin Operations said that millions of alerts in just the first couple of months alone already proved the observatory is up and running as a genuine discovery machine. Teams are using artificial intelligence and machine learning systems specifically designed to sort through this flood of information in real time, because there's simply no way a group of human astronomers could manually review 7 million nightly alerts on their own. The AI filters through the noise and flags the events that matter most, so researchers around the world can react quickly, sometimes within minutes, and turn other telescopes toward whatever unusual event Rubin just detected. This is part of what scientists call multi-messenger astronomy, studying the universe using multiple types of signals at once, light, gravitational waves, and cosmic rays working together. When Rubin spots something like a possible collision between two extremely dense objects, or a sudden explosive event somewhere in the sky, it can immediately alert observatories around the globe to point their instruments at that exact spot, so the event can be studied from every possible angle before it fades away. Supernovae are one of the clearest examples of why this speed matters so much. A supernova occurs when a massive star reaches the end of its life and explodes in a burst of light so powerful it can briefly outshine an entire galaxy. These explosions don't last long. They brighten quickly and then fade over days or weeks, which means if you're not watching the right patch of sky at the right time, you simply miss it. Older telescopes, moving slowly and covering small patches of sky, missed enormous numbers of these events simply because nobody was looking in the right place at the right moment. Rubin Observatory solves that problem by never really looking away, because it revisits the same regions of the sky every 3 days. Every single explosion, every sudden flare, every fading afterglow gets caught somewhere within that repeating cycle of images. The moment the system detects a sudden brightness change matching the pattern of a supernova, It sends out an alert within minutes, giving astronomers around the world the chance to point other instruments at that exact location while the explosion is still unfolding. This is exactly the kind of multi-messenger global teamwork scientists have been dreaming about for years. One observatory acting like a smoke detector for the entire southern sky, and dozens of other telescopes racing to respond the moment the alarm sounds. Phil Marshall, the Deputy Director of Rubin Operations for SLAC, described this entire journey in a simple, honest way. He said it took 20 years of hard science, engineering, and determination just to reach the point where the team could finally say action and start rolling on what he called this blockbuster movie of the universe. He also noted that the millions of alerts generated in just the first couple of months of testing already proved the observatory works exactly as intended, a genuine discovery machine, fully assembled and finally switched on. Mike Brown, a planetary scientist at Caltech who has followed this project since his early days in graduate school more than 2 decades ago, said working with Rubin's data now feels like something he could only have dreamed about back then. Watching a project take shape over 20 patient years and finally become real functioning science. He also pointed out something worth remembering. If you asked 50 different astronomers what they're most excited to find using this telescope, you'd likely get 50 completely different answers. Because this survey genuinely touches nearly every corner of modern astronomy and astrophysics simultaneously, every single night. Over the coming 10 years, scientists expect this survey to fundamentally reshape what we know about our own solar system. Researchers predict Rubin could help triple the total number of known asteroids and increase the number of identified trans-Neptunian objects by nearly tenfold. Every single discovery adds another piece to the puzzle of how our solar system formed billions of years ago, how planets and smaller bodies settled into the orbits we see today, and what forces shape the outer edges of our cosmic neighborhood. But the larger goal, the reason this observatory carries Vera Rubin's name in the first place, reaches even further than asteroids and comets. Scientists are hoping this 10-year survey finally delivers real answers about dark matter and dark energy, the 2 biggest unsolved mysteries in modern physics. Dark matter appears to make up roughly a quarter of everything in the universe, yet we've never directly observed it, only its gravitational fingerprints on galaxies, the very same fingerprints Vera Rubin first noticed decades ago. Dark energy is even stranger, the mysterious force that seems to be causing the universe's expansion to accelerate rather than slow down the way gravity alone should cause it to behave. By observing billions of galaxies over 10 full years, tracking how they move, how their light shifts, and how the structure of the universe evolves over time, scientists hope Rubin Observatory can finally help explain what dark matter and dark energy actually are, something no telescope in history has fully managed to answer. Consider everything this single machine is accomplishing at once. It's mapping our own solar system in more detail than ever recorded. It's discovering tens of thousands of new asteroids, some of which may one day matter for planetary defense. It's catching supernovae the moment they explode, giving scientists a front row seat to some of the most violent events in the universe. It's tracking supermassive black holes as they flicker and flare across billions of light years of space. It's building toward a full catalog of an estimated 20 billion new galaxies. And underneath all of that, it's quietly gathering exactly the kind of data that could finally crack open 2 of the biggest mysteries human science has ever attempted to solve. And we're still only in the earliest days of this 10-year mission. Everything described in this video, the 11,000 asteroids, the record-breaking spinning space rock, the 800,000 alerts in a single night, the trillions of pixels within a single image, all of it happened before the official survey had even fully begun. The real 10-year clock only started ticking on June 30th, 2026. Every single night from here forward, this telescope keeps watching, keeps scanning, keeps capturing data at a scale no observatory on this planet has ever managed before. And somewhere within that flood of nightly images, hidden among millions of galaxies and thousands of newly discovered asteroids, there's a very real chance that Rubin Observatory ends up capturing something completely unexpected, something nobody predicted, simply because it's watching the sky more closely, more often, and in more detail than any instrument in the history of astronomy. Remember, this observatory is only a few weeks into a mission designed to run for 10 full years. Every single one of those years is going to bring fresh batches of asteroid discoveries, fresh supernova alerts, fresh images of galaxies nobody has ever cataloged before, and slowly, piece by piece, real progress toward finally understanding dark matter and dark energy, the 2 mysteries that gave this telescope its name in the first place. If this kind of real, fact-based space coverage is something you genuinely care about, make sure you hit that subscribe button right now, because we're going to cover every major update from this observatory as it happens across the next 10 years. Drop a comment and tell me which part of this story surprised you most. The trillion-pixel nebula image, the fastest spinning asteroid ever found, the 800,000 alerts sent out in a single night, or the fact that this telescope can send out millions of alerts every single night once it reaches full operating speed. I read every comment, and I genuinely want to know which fact made you stop and rewatch a section, because that tells me exactly what kind of space stories to bring you next. And if you learned something new today, share this video with someone who still thinks space exploration slowed down after the moon landing, because right now, in real time, we're living through one of the most productive periods in the entire history of astronomy. And this observatory in Chile sits right at the center of it. Thanks so much for staying with me all the way to the end. I'll see you in the next one.